Thank you. So yeah, it's a pleasure to be giving a talk in this very nice and kind of important conference for 60th birthday of Hubert SALEUR. So it's a shame that I cannot be there, but so I'm currently in Montreal, in the University of Montreal. So I was not able to be in Paris in this time. So just say, so of course I know Hubert for quite some time now. I've never written a paper with Hubert, but my first memory of Hubert is when I just arrived in Oxford, kind of fresh from the group of Nathan Andre, working on quantum impurities and exchanging emails with him. So it was rather impressive, kind of exchanging emails with this big professor, French professor from Saclay. So it was kind of nice. And then, okay, so I continued discussing with Hubert throughout my career at various points. So just want to say, so happy birthday, comme on dit par ici, bonne fête Hubert. So let me start with what I want to discuss about, which is about correlation functions from hydrodynamics. Now, hydro is something that I've been working on now for the last 5 years or so. And it's a set of very powerful principles that allow you to get kind of exact results at large scales of space-time in a variety of situations. Okay, and I want to describe for you here, I mean, let's see how time goes, but at least one thing which is called the Boltzmann-Gibbs principles, which allow you to get asymptotics of correlation functions in space-time, so dynamical correlation functions, and how to go beyond this principle in order to describe bits of correlation functions which are not accessible by this kind of standard principle. Okay, so what I have in mind is Hamiltonian for an extensive Hamiltonian for an infinitely long system in one dimension, for instance, a quantum chain. So think about the XXZ quantum spin chain, for instance, or even more simply the XX quantum spin chain, which is the one that I'm going to be concentrating on for my examples of the general principles. Okay. So the quantum chain has some conservation laws. For instance, any integrable quantum spin chain will have infinitely many conservation laws, as discussed in many talks just before me. So there will be operators satisfying this conservation equation. So there's some density and some currents, and total conserved charge being independent of time. So this is the case for XX model, which is examples I will take, but of course the general principles that I will be describing apply much beyond the XX model, and apply in fact, in principle, to integrable and non-integrable model, because they are based on hydrodynamics idea, let's say. So I will be considering particular states, or correlation functions in states. Now I can consider a wide variety of states, but just for illustration purposes, let me just think about thermal states. So thermal states of quantum spin chain. Okay. So what's the question I'm asking here? It's a very simple question, but difficult technically. So it's the question of correlation functions of 2-point correlation functions of local operators in space-time. So A and B are, say, Pauli matrices evaluated at different points in space and evolved in time. So A is evolved in time for some time t, according to the Hamiltonian of your quantum spin chain. And I'm looking at the connected correlation function, and the question is what happens with these connected correlation functions when both x and t are large. So going far in space-time. I'm looking in particular at what people call the hyperbolic scaling, which is taking x and t both large with fixed ratio x over t. Now this is just correlation functions in space-time. That in integrable models, of course, there are many techniques to evaluate correlation functions, beta ansatz, and the scattering form factors, which I didn't mention there. But even with all these techniques, this question is in general rather difficult. So it is not easy to get the correct asymptotic at large space and time in space-time. At large space, usually it is possible. The techniques are advanced enough to get asymptotic, but with time evolution, this is rather difficult. So that's the question I'm still asking. And so the point that I want to make is that hydrodynamics, so kind of general ideas of hydrodynamics, offer a number of very universal principles which are valid, in fact, at and without, with and without integrability, and which give exact asymptotics. Now they give these asymptotics in terms of some simpler quantities, usually thermodynamic quantities or things like that. And in many integrable systems, these quantities can be evaluated exactly using TBA or using generalized hydrodynamics, which is a theory for the hydrodynamic of integrable system that is based on TBA essentially. Okay. Now I'm not going to go into so much detail of GGE and TBA and all that, because the example I'm taking, the XX model, happily has very simple TBA and GHD, so it would be sufficient to illustrate the principles. Okay? But these are general principles. So the first thing that I want to describe is the so-called Boltzmann-Gibbs principle. Okay? So this has a very simple physical idea behind, which is the idea of projection over on slowly decaying modes. So you want to evaluate this correlation function in some quantum spin chain for some local observables A and B. Okay, how do you evaluate that? Well, the idea of hydrodynamics of the Boltzmann-Gibbs principle, which is part of hydrodynamics essentially, is that, well, this can be obtained by considering this little picture there. So A is like a perturbation of your system at point 0 and time 0. And that perturbation produces waves, and the waves propagate, over time. And then you observe what happens with some other observable B at some other point X and at a later time T. And if the wave has reached that point X at time T, then there's something non-trivial happening. So you have some non-trivial asymptotics. And if it hasn't, then there's nothing non-trivial. So perhaps the correlation function is very, very small. Okay. So basically, you obtain the leading asymptotics by projecting this A onto modes. What are these modes? Well, usually they are identified with the conserved charges of the model. Okay? You propagate these modes in space-time, and then you project back somehow B onto the QJ to obtain the influence of these modes on the observable B. So this is a physical principle, at the basis of asymptotics of correlation functions from hydrodynamics. Right? Now that just describes the leading power of the asymptotic, something like 1/t at large time, because this is hyperbolic scaling, so you should have power law, and usually it's a 1/t at large time. Okay, so it will describe something like that. Okay, so if your correlation function decays faster than 1/t, then that will just not describe it, will give 0. But that gives at least the leading 1/t. Okay. So let me just say a little bit more. So this is a physical principle. It's kind of just words, right? So you've got to put a bit of mathematics and formulas onto it to get somewhere. So in fact, there's some precise mathematics, and I think this is interesting because it clarifies a little bit what we mean, in fact, by especially by these modes QI, which are the conserved quantities. What do we mean by local conserved quantities in an infinite spin chain? And this is kind of a non-trivial problem. Of course, conserved quantities can be constructed by transfer matrix methods. Now, here this is an infinite spin chain, and I want to know, what is the set of conserved quantities that are part of that chain. This is important because here, so I come back to that, there's a projection onto these conserved quantities. So I need to have all of them. So I need to know the projection of A onto all possible conserved quantities. So there needs to be a complete space of conserved quantities for this to be an exact asymptotic, right? Okay, so what is the mathematics is not too complicated. So basically, what you look at is not quite the 2-point function in space-time. Here, this is in space, but the Fourier transform of this 2-point function with wave number k. And so if you're looking at large space, that would be small k. So k goes to 0. Okay. And the objects that you will need to actually construct your projection, one of the main objects is this susceptibility, the static correlation matrix, so which is the correlation function, the space integrated correlation function of the conserved densities. And I'll come back to what I mean by the space of conserved densities, but for now, you think about the usual conserved densities of your integrable models. Okay, so you construct this matrix, which is just space integral 2-point function of conserved densities. And then what do you do? Well, you want to look at the hyperbolic scaling, so the large time, large space limit, or large time, small wave number limit of this Fourier transform 2-point function. Okay, so in fact, it's a bit difficult to prove anything about these limits. There's no theorem needed that the limit exists or anything like that. But you can define a generalized limit, in fact, something called a Banach limit, which is just taking the time. So you first take the time average of whatever function you have of t and k, and you look at this time average for t being very large, and you evaluate your function at time t and then wave number kappa over t. So wave number is small, time is large, but you kind of average over time to average things out a little bit. So you take that limit. In fact, that limit is not guaranteed to exist, but you can define something called Banach limit by some extension theorem in Banach spaces. So this is a well-defined object, which that thing is guaranteed to exist and to make sense. In fact, it's not a unique object, but it's guaranteed to exist. Okay, and then you take this Banach limit, which is kind of a hyperbolic scaling of your correlation function, and the theorem is that will dissatisfy the hydrodynamic projection. So the little picture I gave in the first slide is actually has an exact mathematical formula, which is that formula. So basically, the first bit tells you to project your operator on the conserved charges. So this is this space integrated two-point function. This object is just space integrated two-point function with k equals 0. And projecting, well, this basis of conserved charges is not necessarily orthonormal, so you need to put the inverse kind of a correlation between these conserved charges there. So the inverse of the matrix form of space integrated correlation function. And then what you have in between is the propagation of these conserved quantities, which is, again, that special limit applied on a two-point function of conserved densities. Then you project back over the operator B. So what this tells you is that you have a reduction of the number of degrees of freedom. This holds for any operator A and B. And what you write, well, you write that special limit of this Fourier transform two-point function for any operator A and B in times of the same special limit for conserved densities Qj and Qm. So if you usually have less conserved density than you have local operators. Okay? So that's actually a theorem. Now, if it's a theorem, it's got to be kind of precisely defined. So in fact, this thing is like an inner product, can be made into an inner product on some Hilbert space, and the Hilbert space is formed out of your observables on the chain and can be interpreted as a Hilbert space of extensive homogeneous observables. So there's actually a well-defined Hilbert space associated to that. And the time evolution of your chain gives a unitary operator on H, and that's the crucial bit in order to have a theorem so that can be shown. And then the conserved charges are nothing else but the intersection over R time of the kernel of this time evolution. So anything that is invariant under that time evolution in that Hilbert space. So it's kind of a well-defined quantity. This thing is itself a Hilbert space. It's a closed space of H. And then you can do projection without any problem. So there is here a rigorously defined set of extensive conserved quantities. And these are the conserved quantities you need to project onto in order to have this Boltzmann-Gibbs principle, which has this simple physical kind of interpretation. Okay? So given a quantum chain, the point is, what are these conserved quantities, or what is the basis, say, for these conserved quantities? In general, for integrable systems, well, Q is infinite dimensional. That can be shown to be infinite dimensional, just on the standard, transfer matrix construction. But for chaotic system, it is conjectured to be finite dimensional. So there's just few conserved quantities, like just the Hamiltonian, for instance, and nothing else, right? And but it is not proven. This is a rather non-trivial thing to prove. Okay. So this is kind of theorems about the Boltzmann-Gibbs principles. It's nice to have mathematically precise formulation for that, and that tells you about asymptotics of correlation functions. But it'd be nice to have a more kind of applicable formula. So yeah, so I wanted to say, so as a last bit, in fact. It is also possible to show that these conserved quantities that are well defined, if they are local, with the appropriate definition of local, they always have a current. And then the two-point function of conserved quantities satisfy a nice evolution equation, which is nothing else but the equation you would obtain by doing a linear response of the hydrodynamic equation associated to this conservation laws. So this is just kind of linear response equation, but written more precisely. This can also be proven rigorously. Okay. Now, so if you put all these kind of things together, you can write the result in a slightly more physically transparent way. And here the way of writing the result, which is more physically transparent. So what this Boltzmann-Gibbs principle actually says, it says that if you are to evaluate a two-point function of local observables, well, what you can do so in order to get the asymptotics from the Boltzmann-Gibbs principle, since we're doing kind of time averaging and small wavelength, small wave number limits. So actually what this corresponds to is taking some average over a large fluid cell. So the principle tells you that if I take my two-point function now in space-time, instead of doing Fourier transform, but doing average in fluid cells, so at large, kind of this fluid cell has size r in x in space and r in time, and r is taking very large, but much smaller than the scale at which you evaluate your point x and t. So the scale is L here, Lx times Lt. So when you take this limit where L is very large and r is very large, what the principle tells you, it tells you that this two-point function should decay like 1 over L. It should decay like 1 over L times the coefficient. And the coefficient is exactly that projection. So it involves integrated correlation function where you have the operator A and the conserved quantities, some inverse matrix of two-point integrated correlation functions of conserved densities, and some delta function, which comes from doing the inverse Fourier transform of what I had written previously. So delta function, and the delta function involves a particular matrix A. This matrix is called the flux Jacobian, and it was defined here, so in that equation. So this matrix A is nothing else but some integrated two-point function of current and densities times an inverse matrix C. So it's all things that are calculable by just integrating two-point functions in space without ever needing time evolution. So this formula is a formula that involves objects that are just defined in space without needing time evolution, and it gives you the large space-time limit of correlation function. It tells you that this correlation function should decay like 1 over L. Okay. So it is important that you must do an average over fluid cell in order to get the actual results, so the actual prediction. Once you do that, this is a prediction. So this is kind of a very a powerful result, right? It's based on hydrodynamic principles, kind of little waves traveling. It has a theorems behind it. Okay? Now, the way it is written here is not completely rigorous, but the way it is written in terms of Fourier transform is rigorous, and it simplifies a lot the job of calculating the large space-time limit of two-point functions. It tells you that you can calculate all of that just by calculating objects which are space integrated at time zero, two-point function of the observables you have in the conserved densities. Okay. Now, this can be applied to integrable systems, so it'd be nice to have something a bit more kind of explicit, so to compare, right? So this formula, where there's the inverse matrix of space integrated densities, the matrix A, which involves the currents. So this formula all the objects in there can be calculated in integrable systems. So C is known from the thermodynamic Bathian side. So actually, this is quite old results. It's from the old results of the 60s and 70s. You can calculate this matrix. A is known from generalized hydrodynamics. So this is essentially from the exact evaluation of current. So that's from 2016 onward, where this matrix A was evaluated. And these overlaps, well, they are, if you think about it, just variation of averages of observables in GGEs with respect to parameters in the generalized Gibbs ensemble, the parameter that is associated with the conserved charge Q. So basically, the GGE has the form exponential minus sum over I beta I QI, where these are the conserved charges. And of course, if you do the beta derivative, that brings down the total charge, and that gives you the integrated two-point function of the average of A and the charge, okay, the charge density. So that's kind of so these are all equilibrium objects, if you wish, and you can calculate that using methods of integrability. In particular, if you evaluate two-point functions of conserved densities, Q and QI, QJ, any conserved density doesn't matter. Well, there's an explicit formula with objects that are fully given by TBA. So one of them is the root density. So this is the beta ansatz root density. This N is beta ansatz occupation function coming from beta ansatz. This effective velocity is something that comes from generalized hydrodynamics, which is related to the exact evaluation of currents. And these HI and HJ are simply the one particle eigenvalues of the conserved charges corresponding to QI and QJ. So this satisfies something like that. So QI on the state of momentum K is HI of K on that state. And the dressing, well, it's just the thermodynamic Bethe-Ansatz dressing operation. So these are all TBA operations. So integral equations can put that in a computer and you get an exact asymptotics. So this is kind of a nice result. You can, for instance, this result is immediately applicable to the Liebniger model, for instance. But let me check what happens in the XX model, right? To check if this actually works, and it should work, of course. Now, the XX model is rather a simple integrable model because by the Jordan-Wigner transformation, it's a free fermion, right? So the effective velocity is very simple, 4 sine K. Sigma 3, the sigma 3 matrix evaluated at point X can be written in terms of free fermions. So these are just free fermions coming from the Jordan-Wigner transformations. So it is, in fact, this is the fermion number. So fermion number density, so sigma 3 is actually a conserved density. So I can immediately use this formula, just applicable, applied it to the XX model. The result is that what I get for xt large at a fixed ratio x over t, I get that this two-point function should have this particular asymptotics. So it's a 1 over t, so instead of 1 over L here, right, there's 1 over t, and a function of psi, which with non-trivial kind of occupation function involved there. Okay. So this is the prediction from hydrodynamics on this simple quantum spin chain, just using hydro and the integrability structure of the spin chain. But we can compare with an exact calculation, of course. So by direct Weik's theorem and saddle point analysis, this 2-point function can be evaluated because these are simple bilinear fermions, and the model is a free fermion. So this is just a Weik theorem calculation. So it's kind of very simple calculation. I didn't need hydro to get prediction. You can just calculate it. And what I find is an answer that is slightly different. I find something that looks similar to what I had plus an oscillatory term. But what I should remember is that the Boltzmann-Gibbs principle tells you to take the fluid cell average. Once you do the fluid cell average, you kind of delete any oscillatory term, and indeed you get back to the Boltzmann-Gibbs results. In other words, this very nice, powerful result from hydrodynamics gives you 1 bit of the actual asymptotic of the 2-point function of this observable, gives you the bit that is non-oscillating. But it gives you the correct one, so that kind of checks the general principles and the general formulas. Okay. Now, there's other observables that we can look at in this XX spin chain to check if things work. So, for instance, the sigma plus sigma minus, right? So sigma x plus I sigma y in this spin chain. And these, by the Jordan-Wigner transformation, are related to the creation and annihilation operators of fermion operators, right? Up to a Jordan-Wigner string. Well, because the conserved charges in the XX model, they have the form of C dagger C, where C is just a Fourier transform of A, so they are just kind of free fermion conserved charges. So fermion occupation numbers at mode K, these are the conserved charges, and that's it, right? These are the extensive conserved charges. Well, because this has a creation operator, this overlap, which is now a 3-point function, A dagger and A dagger A, that is 0, just by fermion conservation, actually. So this has 0 overlap. Exactly. So the Boltzmann-Gibbs principle then will tell you that this asymptotic should go to 0 because it's 0 overlap. Of course, you can do also a computation of this 2-point function from the XX model, so macroscopic calculation. This was done originally by Itzek and Korpin-Slavnov using Fredholm determinant, and you find exponential decay, which is subleading to Euler. And exponential decay, well, it's subleading, so it's much smaller than 1/t. And so indeed, this agrees with Boltzmann-Gibbs results. You get 0 because you get something that's much smaller than 1/t. So you see that the Boltzmann-Gibbs is nice, powerful, but it doesn't give you everything about correlation functions. It kind of omits anything that is oscillating. So it gives you the monotonic algebraic decay, but anything oscillating, it's been washed out by the averaging. And anything exponential, well, is much smaller than 1/t, so it doesn't give you that. So the question is now, are there general hydro principles that will give you these 2 other things? So can you go a bit beyond this standard principle of hydrodynamics, where you just project over propagating waves and describe something that is oscillating and describe something that is exponentially decaying? Okay, so that's what I'd like to convince you of by using the example of the XX model. Okay? So what are the general principles? Well, it's very interesting. So the mathematical construction, kind of the mathematical result I told you about Boltzmann-Gibbs principle, in fact, can be extended very easily to different definitions of what we call time evolution and what we call space translation. You can put there some frequency, some omega, and some different wave numbers, some k. And you can do the whole construction using these different formally defined time evolution and space translation. And this, so essentially, now you redefine what you mean by conserved quantities. They are not the ones that are conserved under usual time evolution, but under oscillatory time evolution. And you redefine what you mean by homogeneous in space, so invariant under space translation. They are homogeneous, but under oscillatory space translation. And then with this redefinition, the whole theory applies. So essentially, you can do hydrodynamic projection, but with respect to a different wave number and a different frequency. You just have to redefine all your quantities. So essentially, the new fluid cell averaging now is an averaging with respect to oscillating space and time. The new susceptibilities are space integrated with an oscillatory factor. And the new conservation equation are not that the charge should commute with h, but they should commute with h up to a frequency. And if you do that, so basically what you obtain is the same formula as we had, but with different objects defined with respect to different frequencies. And that tells you what happens when you do an average with respect to frequencies in space and time. So you can check what happens with the XX model. In the XX model, it turns out that you can construct this particular conserved charge, which is a creation operator for a discussion operator for a mode at a certain k and a creation at a different k. And the k's are chosen such that these two modes have the same velocity. So the velocity in the XX model is non-monotonous, monotonic in terms of the k's. And so for any given velocity, there are 2 points which have the same velocity. And so you put them in there. And it turns out that's just the right conserved charge for this frequency dependent hydro projection. And that tells you exactly, that recovers exactly the correct frequency, the oscillating part of the 2-point function that you had gotten by a simple Wick theorem calculation. So that illustrates a general principle that you can do finite frequency hydro projection to give the correct oscillatory algebraic decay. So it's kind of a new type of hydro, but around a different point in the in the space, in the k omega space. Instead of being around 0, it's around some finite point. So in principle, this is applicable beyond the XX model, but for now, we know what are the charges for the XX model. Some of the new charges that Vincent was talking about actually might do the job for actually truly interacting models. Yeah, so this is kind of a hydro principle that allow you to get to non-trivial oscillation. So you can even go beyond the Boltzmann-Gibbs principle. It's very similar to Boltzmann-Gibbs principle, except it's a different set of conserved charges and different set of different notion of homogeneity that allows you to get oscillating bits in your 2-point functions. Now, what about exponentially decaying bits in your 2-point functions? Well, that's a little bit more difficult. In fact, you need to kind of change quite a bit the theory to get something there. And the principle behind that is the principle of twist field. So a twist field is something that can be defined in whenever you have conserved densities and conserved currents. So it's something that is that pertains really to conservation laws and actually hydrodynamics. Okay? And the idea is that you can define formally a field, a height field, which is simply related to the conserved densities and conserved currents by derivative with respect to x and with respect to t. This is formally defined. So if you want to calculate its 2-point function, well, essentially the 2-point function of the exponential of this height field, so this bit is called a twist field. So I should say this thing, the exponential of this height field, is called a twist field. So the 2-point function of such twist field, well, basically you can rewrite that as an exponential of an integral over space-time where you integrate the perpendicular current along the trajectories from 0, 0 to xt. And because the 2 current qj is conserved, well, this integral does not depend on the shape of the trajectory. And so you see that actually this object just depends on the point 0, 0 in xt, and that kind of allows you to say that there's a field at 0, 0 and a field at xt. Yeah, this is a twist field usually denoted t of x comma t. So, okay, so this is a construction you can do whenever you have conserved quantities. Now, remember that by the Jordan-Wigner transformation, sigma plus had this form. So there's a dagger and then there's exponential of a fermion density. So this looks a bit like a twist field. You have exponential over a path over x of a fermion density. Well, it turns out that the 2-point function, sigma plus, sigma minus, can be rewritten exactly in terms of such twist field. So there's the creation and annihilation operator that are there. And then there's an exponential, the Jordan-Wigner string, of an integral of the space-time, the 2 currents on space-time of this conserved density, which you can write into the phi 0 xt and phi 0 as 0, 0. So my phi 0 here, the 0 means that I'm looking at the conserved fermion density. So this is this object there, this object is e to the I pi phi minus phi. Really, what it means is that exponential of integration of currents and densities, and these currents and densities are explicitly written in terms of Fermi bilinear, of course. Okay? So this is a space-time Jordan-Wigner string, and this rewriting now allows you to do some hydrodynamics and to obtain exponential decay of this 2-point function. So basically, the quantity, this quantity, the lambda integration GQ, can be analyzed using large deviation theory. So you look at when x and t are large, and what you expect is that this should go like an exponential of the scale at which these are large times some function that depends on lambda and on x and t. And this function can be evaluated by using Euler-scale macroscopic fluctuation theory, something that was explained in Takato's talk yesterday, I think, or by using what we constructed something called ballistic fluctuation theory. So there are ways of calculating this function exactly solely in terms of objects from Euler hydrodynamics. So the matrix C and the matrix A that I've introduced before. Okay? So you can work this out. So there's a way of working this out. The basic way is to say, okay, so if you introduce this exponential, you kind of change the state, and the state becomes lambda dependent. And this new state is actually a GGE, and the GGE satisfies a certain flow equation, which you can is defined by a flow equation on its Lagrange parameter. So the GGE has the form again even minus sum over I beta I of lambda qi, and so that state represents the insertion of this exponential. And where the beta satisfies this equation, you see there's the A matrix that I defined previously, which is involved, which is essentially the overlap of the current with the conserved densities with the inverse static correlation matrix. Okay. So this is A. So so basically there's a way of writing. Yeah.
That we have still 8 minutes, and you certainly want some questions.
Yeah. So I'm kind of finishing in 3 minutes, I think. so you have these flow equations there, and independently of the details, you can work this out. So the F then is written in terms of the average currents and density along that flow. You can work this out in the XX model rather easily. So basically the GGE is written explicitly in terms of the energy of the modes in XX model and that velocity that I introduced. And the F is explicitly written as an integral over the mode with some particular function. So this is essentially a generalization of the free energy to time-like domain. Okay? And now what you say, well, you say, okay, so now I have to evaluate this object, and this object is controlled by the two-point function of these fermions, in this modified state, this GG kind of that depends on lambda introduced by this parameter there, times the exponential of that large deviation function, which tells you about how just that exponential would decay as L is large. So you have so that exponential of this of this function actually tells you about spin transport. Is a large deviation function for the transport of spin along that line, while this two-point function is just a fermion correlation function in this very special state. So you have two contributions, and both of them can be evaluated here by using this ballistic fluctuation theory, and that explicitly, if you wish, by using Wick's theorem. In fact. So you get the result, and this is kind of my kind of big slide result, if you wish, just the final slide. So it's rather a complicated result, of course, but interestingly, you get indeed the exponential decay. So hydrodynamics is able to predict the exponential decay. So you recover formulas that were found before by using Fredholm determinant analysis by these people, asymptotic Fredholm determinant analysis. But I have to say the way that we recover that is, of course, much simpler. I mean, the Fredholm determinants are rather complicated. And you also get a new formula in a parameter regime, which was never written before in the literature, apparently. So when you look in space-time for in space-like regions, so this is space and time, there's kind of x and t there, and this is x equals 4t. Okay? So if you look in space-like region, and for magnetic field greater than 2, well, nobody had actually written the asymptotics in that case, unfortunately. And but we do find the asymptotics using hydrodynamic principles. And interestingly, there's kind of an extra term that is kind of non-trivial that comes from the structure that we have from our hydrodynamic predictions. Okay? So we find the exponential decay of this two-point function in the full range of domains in space-time and in our values of magnetic field. So that's all kind of I wanted to say. So this is numerics that checks this formula. So basically, this is kind of a new formula coming from hydrodynamics. This numerics that check the formula, so that works pretty well. And so as a conclusion, hydro projection allow us to get the kind of 1/t asymptotics of correlation functions, but one can generalize that to frequency hydro projections, and one can also do exponential decay using hydrodynamic ideas. Thank you for your attention.
Yeah, thank you for the nice talk. There are questions, yes.
So the in the Lieb-Lineker model, so the creation operator, is it a twist field in your sense? And if so, what charge do you have to use?
Yeah, so thanks, Jerome. I knew precisely you were going to ask this question.
Okay. Well,
no, thanks. But this is an excellent question, and that's something that I'd like to work on, and that I have some ideas for what the charge is. So the creation operator, say the bosonic creation operator of Lieblinger model, for instance, psi, dagger, right, is some kind of twist field, but is rather non-trivial indeed to determine what kind of twist field it is. Now, my understanding is that basically the leading exponential decay would be controlled by fluctuation of phases of this field. So psi, is a complex field, it has a phase, and this phase fluctuates a lot, and that will provide leading exponential decay if, whatever regime where there will be leading exponential decay. And this phase is related to very special charges in generalized hydrodynamics, which I think are the ones that we discussed in our paper on quantum GGE. So I think there's a way of applying this method to the psi 2-point function Lieblinger model by this appropriate choice of charge. Yes.
Other questions? Maybe I also ask. I mean, somehow you suppose that dynamical exponent is 1, so that's rotational invariant somehow. I mean, it's a lattice after all. So but, I mean, apart from that, and you only get out one function which decays like 1/t, which is much less than what you have, for instance, in standard conformal field theories. You have other exponents. This is baffling to me. Can you explain?
Yeah, so it's also a very interesting question. Okay, I didn't have time to go in details of that. In fact, 2-point functions do not necessarily decay as 1/t. Now, this is not conformal field theory because I'm looking at finite temperature, and if I look at 0 temperature, well, there is a similar theory that will apply, but of course, it will be related to CFT and all that. And I don't know the full structure there, but certainly even at finite temperature, away from conformal point, you may have other exponents. You may have one of the square root of t, for instance, for diffusive system. A lot of time you have one square root of t, or one over t to the 2/3 or something if you have KPZ or things like that. Okay. And what is actually happening there? Maybe I go back to very quickly to the formula to tell you what is happening. So the XX model is kind of overly simple. There is this formula there, right? There's a delta function, and in many models, this A matrix actually has a discrete spectrum. So what you have is a 1/t times a delta function. So the prediction of Boltzmann-Gibbs tells you that the 1/t coefficient at certain velocity will be infinite. And so basically that means that it's not 1/t anymore. It's weaker than 1/t, like 1 over the square root of t or any other exponent. And Boltzmann-Gibbs does not tell you what the exponent is. You need to go a bit further. That's another kind of area of expansion of hydro principles, to get into this, what are the other exponents? And of course, there you might want to introduce diffusion, spread diffusion, KPZ, and all that. So this is, it just tells you, if you find infinite times 1/t is some other exponent, if you find 0 times 1/t is another, but kind of a more decaying exponent or exponential. That's what it tells you.